Thank you. Good morning, everybody. Thanks for joining here in the room and to those online for joining. It's going to be pretty interesting if the clicker doesn't work because I have a lot of animation, so we're going to work together to make this go as smooth as possible. So I'll give it a test. No. All right, go ahead and hit the next slide, and I'll begin talking about that I do field work. I'm a postdoc at Howard University and NASA Goddard. And I'm working with the RISE 2 team. So Nick and Ernie before gave a great introduction to the field site, but I'm going to talk about a unique tool that I've been developing to help with some data visualization in the field, both during analog scenarios and potentially into future planetary deployments. So, oh, there you go, that worked, thank you. So out here I am in the office collecting some data. That's a handheld spectrometer, one of the handheld instruments we use on the RISE 2 deployments. Up at the north rim of Kilburn Hole and some of those surge deposits. And in the background is my colleague Alice Baldridge. Oh, it gave me one click and that was it. Must be a dying battery. Next slide. She's also collecting some data in the background there. And one of the problems we run into out in the field is that the data we collect on these different instruments tends to get siloed either within the instrument or within the computer that controls that instrument, usually until we get back to the lab and are able to download things and share them with each other. And that data isn't just, if you can hit the next like 3 or 4, it's gonna animate a few things. It's not just compositional data, but it can be metadata like the location, the elevation. One more would be the time that that data is collected. And this is all great information that you might want in real time if you're trying to run an analog mission scenario or a real mission scenario. So the tool I've been working on is a way to sort of get that information out of those instruments and apply it right to the field site itself. Next slide. So one way of doing that, which we've seen a few times here in previous talks the other day, is using a GIS, something that displays things in a map view that can put in pins for, next slide, different locations where you collect data around a feature such as Kilburn Hole. But what we do in geology is often focus on a single outcrop, which, next slide, tends to look like something like this, a vertical transect across multiple layers, which when you try and plot on a map view like a GIS, next slide, tends to bunch up the points into one location. Oh, some more technical difficulties. There you go. So yeah, just an illustration of how that might look in a map view. So what we're working on is to use augmented reality to turn the outcrop itself into sort of a virtual display, a vertical GIS, you might say, which, next slide, you could interact with in the field and get the data right from the outcrop itself. So you might ask, what is augmented reality? You may have experienced this. You can hit next a couple times here. Applications like this have popped up over the last few years where you can essentially use a smart device, a tablet or a phone that has a camera embedded in it to view the world like you were going to take a photo, but then overlay a digital asset into the scene. What those apps tend to do is look for a flat surface like a floor or sometimes a wall to anchor those analog or digital assets into the scene. But in the real world, next slide, geology tends to be a bit more rugged, a bit more complex morphology. So it's a bit harder for your standard augmented reality app to link into a real world view like this. But luckily, next slide, we can use a tool such as this, one more next, like a BLK360 small LiDAR scanner to view the world not just as a photo, but as a morphologic point cloud. So next slide, that sends out a bunch of laser beams, it bounces off the outcrop, I'm sure you know how LiDARs work, and essentially creates a 3D representation of the terrain, which we can turn into a shape model and then link the data directly to the shape of the outcrop itself. So next slide. So this brings us to a quick 3 phases here to go through. The first is a proof of concept. In order to test this out, I needed a test rock, a test location that was fairly well controlled. It wasn't going to change environments too much, just fairly standard lighting conditions. And luckily at Goddard, we have such a rock in building 33. In the atrium, there's this large rock mounted to the wall. And you might ask, why is this rock there? Why are you not allowed to touch it? It turns out when they were building the building, they excavated this and it contains a ton of dinosaur footprints. You can kind of make out a few in this view, but it's a prime candidate for something like augmented reality to really view additional features which you might not be able to see with the naked eye. So next slide, took the LiDAR scanner over to that building, did a great scan, kind of hard to see in this lighting, but it's a great 3D representation of that rock itself. Next slide, which we're able to, you can hit next a few times here, one more. Take that model, throw it into some programs. We're using Unity, which is a game engine to handle the virtual assets, and a plugin called Viewphoria, which handles the camera orientation and tracking of those objects in real time. to create essentially a digital model with virtual stickers applied to it that represent those data in the correct location. So next slide, what that looks like, if you record the screen, which I did, you hold up your tablet to the rock itself, and those stickers apply in real time to the surface that they're meant to go on. So now you can see there's a lot of dinosaur footprints, and I'm no paleontologist. I actually borrowed these from a paper that was published on the rock. I just happened to create the virtual assets for these. But they stay in place even if you move closer to the rock, further away, left or right, just like you would in the field. You can get up close, kind of work with the rock, but also view that data where it's meant to be. And this really helps. I personally didn't notice all these smaller dinosaur footprints before doing this, but then they're there. And even what this video doesn't capture is that you hold up the tablet, and with your naked eye, the rock itself doesn't change, but you're able to tease out some of these features. So next slide. What this also does is that since these are virtual assets, you can link additional data to them to the rock itself. So in this case, an example of the dinosaur that made that footprint could be tied. A link to the Wikipedia page can be linked right to the rock itself. So next slide. And perfect. So that worked pretty well in essentially the lab, but we wanted to try this out in the field. So in May, one more next slide, we got the chance to head to Lava Beds National Monument in California to explore some lava tubes, which are a great candidate for this type of thing because they're essentially enclosed set of walls that you can scan with a LiDAR and then apply data straight to those features. Next slide. So this is a cross-section. This is an older LiDAR scan of one of the tubes out there. It's called Skull Cave. You're seeing it sort of side on if you were buried in the earth looking at it. It's a LiDAR point cloud. It kind of parallels the surface and then drops down a little bit. And the goal here with this expedition with the Goddard Instrument Field Team was to move along through the cave, take handheld instrument data at several locations, next slide, which are represented by these orange dots. And at those locations, either collect new LiDAR scans or use the pre-existing LiDAR scans to, again, create a virtual representation of the rocks that you could link the data to. And then by the end of the field expedition, take the data that you just collected and view it in real time right on the rock. One more, next slide. So what that would look like, and you can hit advance one more time, is as you move through the cave, when the iPad or tablet sees that location where data has already been collected, it automatically displays right on the screen. Next slide, you can interact with that and then view, say, a spectra of the rock there. So this is what we tried to do. Next slide, we set up the LiDAR in a lava tube, or several lava tubes actually. We got some great scans, and a special shout out to Dan Cremens and Kayla Berry for helping out with this field work. We covered a lot of ground that week. Next slide. And so there's Dan himself using the handheld spectrometer to collect data right on one of these rocks inside the mouth of Skull Cave, which, next slide, we were also able to collect the LiDAR scan for, so you transition from the physical to the virtual. Next slide, overlay the location for all those points in the correct location that corresponds where it was collected. And then, next slide, you're able to view the handheld spectrometer spectra that we collected just a few days before in the location. So this would be helpful if another team member, you could hand the iPad to them and they're looking for a sample that has slightly more of one mineral or features a specific dip in the spectra. They know that this is a better area to sample. Unfortunately, due to some technical glitches earlier in that field trip, not with the AR app, but just with access to computers and internet type things, we were only able to do this one section of the cave. But as you can see, it's much larger. There's other field team members in the background for scale. Things jump around a little bit when you move back, but the data stays in place where it's meant to be. So this is a really good, again, proof of concept for moving. Yep. Okay, so last slide. This is just a different view of what it looks like if you're holding the tablet, but we don't need to dwell on this. Future work, where we're going to apply this next. Next slide, and you can hit advance twice more. That'll bring us to the end. We'll be heading back with GIFT to Hawaii in September, another lava tube where we're helping to expand on this and really hand this to other teams as a tool for helping to guide location of data collection. We're working with the RISE-2 team back in the Portillo volcanic field, potentially integrating this into some analog astronaut deployments in the future. And then we're happy to announce that we were selected for a P-STAR project. So over the next 3 years, we'll be working with the Aardvark augmented reality data visualization analog research campaign to really integrate augmented reality into the forefront of both a rover and an astronaut mission. So with that, I'll end there. One more slide advance. Thanks for listening. If you have any questions, my email's on the screen, and I don't know if we have time for questions, kind of got sidetracked with a few technical glitches, but thank you very much.